In this video, we're diving into the fundamental concepts of time and ordering within distributed systems. We will explore how these systems handle the challenge of establishing a consistent order of events when there isn't a single, reliable clock to synchronize everything. We will discuss logical clocks and vector clocks. Logical clocks provide a way to order events without relying on physical time, while vector clocks help in capturing causal relationships between different events. Let's address the core challenge, the time problem in distributed systems. The primary issue is that physical clocks are fundamentally unreliable. In a distributed environment, it's virtually impossible to maintain perfectly synchronized time across all nodes. This is due to several factors, including network delays, the inevitable drift that occurs in hardware clocks, and the inherent limitations in coordinating separate systems. Because of these challenges, we need alternative approaches to understand the order in which events occur. Let us introduce the concept of logical clocks. A logical clock is a mechanism designed to capture chronological and causal relationships between events in a distributed system. The beauty of logical clocks is that they accomplish this without depending on physical time. Instead, they rely on the internal logic and event sequencing within the system to establish order. The abbreviation LC is used to represent logical clocks. Here is an algorithm for you. Lamport's logical clock algorithm. This algorithm is a classic approach to implementing logical clocks. Each process in the distributed system maintains its own logical clock, denoted as LC. When an internal event occurs within a process, the process increments its logical clock. When a process sends a message, it first increments its logical clock, and then attaches the current value of its clock as a timestamp to the message. When a process receives a message, it updates its logical clock by taking the maximum of its current clock value and the timestamp in the received message, and then increments the result. Here are the rules for Lamport's logical clocks. On internal events, increment the logical clock. When sending a message, increment the logical clock and attach a timestamp. When receiving a message, update the logical clock to the maximum of the current clock value and the timestamp, and then increment by 1. Now let us explore vector clocks. A vector clock is an array or a vector of logical clocks. There is one logical clock for each process in the system. It's designed to capture the causal ordering of events across all processes in the distributed system. This means that, unlike Lamport clocks, vector clocks allow us to determine not just if two events are ordered, but also if they are causally related. Here is the algorithm for vector clocks. Imagine that process I maintains a vector clock named VC, which is an array of length n, where n is the number of processes. When an internal event occurs, process I increments the ith element of its vector clock. When process I sends a message, it first increments the ith element of its vector clock, and then attaches a copy of the entire vector clock to the message as a timestamp. When process I receives a message, it updates its vector clock by taking the element-wise maximum of its current vector clock and the timestamp in the received message. Finally, it increments the ith element of its vector clock. Here are the rules that needs to followed while using vector clocks. On internal events, increment own clock. When sending a message, increment own clock, send vector. When receiving a message, element-wise max of current clock and timestamp is computed and increment own clock. With vector clocks, we can implement causal ordering using the following comparison logic. Event A happen before event B if and only if A is less than or equal to B, and A is not equal to B. Concurrent events are those where neither A happened before nor B happened before. The key advantage of vector clocks is they capture causal relationships between events. Also, they detect concurrent events that Lamport clocks cannot and enables consistent ordering across all processes. Here is the summary of the video. Logical clocks enable simple ordering without causal detection, whereas vector clocks enable complete causal ordering and concurrency detection. Both logical and vector clocks have numerous real-world applications. They are used in distributed databases and consensus algorithms, event sourcing and command query responsibility segregation, CQRS, systems, distributed version control systems, and blockchain and cryptocurrency protocols. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.